Okay, everybody, let's go ahead and get started. Welcome to another fabulous installation of the Seattle FSharp user group / meetup. I see a lot of people here who I've seen before, a couple of new faces. So if you're new, welcome. And if you're here before, I'm surprised to come back because if we're not, we don't have our stuff together as well as we could. We have a couple of talks today, a short one about FSharp open source status from Kevin on the Visual FSharp team, and then Curt, who's FSharp user group regular. He's got a talk on some of the FSharp stuff he's been doing at his work. And that'll be a bit longer afterward. Random bookkeeping stuff. If you're not on the meetup group, please join. You'll get announcements about future meetups, future events. Then, very unrelated thing, if you guys aren't aware, there's been sort of this community push to get a new logo design for FSharp for use sort of throughout. There isn't really an official logo right now. There's kind of Microsoft logos that are very Visual Studio specific, but there's no cool logo for FSharp as a language. So there's been a little bit of a push recently to get one designed. I'll send out a link later to the meetup group, but if you guys want to check that out. I think there's going to be one more round of voting. There's been a couple of candidates proposed already. So I figured you guys might be interested. Okay, so let's go ahead and start with our talks. The first one is from Kevin. Like I said, he's on the Visual FSharp team at Microsoft. He's been at Microsoft for about 15 years. He's worked on a lot of teams. He's a great guy. I've known him for a couple of years myself. And so let's turn it over to him with a round of applause.
Hi. I have no idea how to do anything technical, so I'm just going to sort of wave. There you go. So I thought I'd start off just by recapping FSharp's open source history, because around here we talk about FSharp open source as if we just started it and just done it. But the truth of the matter is FSharp's been open source pretty much as long as it's been productized. 2010 was when we first really shipped FSharp as a product. There were previews before that, I believe. But that same year, FSharp was open source. November, I believe, the 4th or something like that. It was open source as the Powertools on Codeless, FSharp Powertools. That had the compile, pretty much what we've got open source today. It had pretty much. 2012, VS did another round of improvements for Visual FSharp. Type providers, I believe, was the big cool thing at the time, and the Power Pack was updated with the latest compiler. Source code, support trail, type providers and the like. In 2013, in Visual Studio 2012, the numbers always get me confused. It's we added netcore support, so it's support for the Windows 8 profile, but almost all of our effort went on being able to ship FSharp outside of Visual Studio. Prior to that, FSharp was deeply embedded in the Visual Studio build shipping mechanism. It was a lot of work that the team did in order to enable us to ship FSharp outside, decoupled from the multi-year Visual Studio release cadence. So that was our big 2013 effort. The open source compilers were all updated, and again, the open source community was using the very latest bits. This year, in January, we got to do our first release outside of Visual Studio, so we was very happy about that. We ship in Visual Studio, but we can release more often. And in January, we shipped a small set of updates just to prove that we could do it. And then in April, we suddenly got the open source religion, obviously, and open source FSharp. Oh wait, it was already open source. What we in fact did in April was we said, you know what, these guys are smart. We should allow them to provide some stuff for us. So that's this year's big thing. In late July, early August, we'll be shipping our first out-of-band release that contains open source contributions from the community. We're pretty psyched about that. That's something we've never done before, and for the longest time we didn't think we'd be able to do it. And it was fun. But we're going to be able to do that. We've got support all the way up throughout DevDiv in order to be able to do this and to make it, which is great. What's just about to come is we're just about to open source all the rest of the Visual FSharp stack except the installers. So the project system, the editor, Visual FSI, the property pages, they're all going to be open source, and you guys will be able to get out there and play with them. Hopefully fix them. You will discover that one of our little secrets is that the FSharp project system is written in 3 different languages. So we've got some VB, we've got a lot of VB, we've got some C#, and we've got a lot of FSharp. So you guys are going to learn how to program all the managed languages, hardcore stuff. And yes, the code review went out this week. We're just figuring out the last bits and pieces of it. But what you will be able to do when we do that is you'll be able to install a V6, and that V6 will replace the Visual Studio FSharp components. You'll be able to debug it under Visual Studio. You'll be able to do what you do on the Visual Studio. If you break something, just uninstall the V6, and it goes back to the Visual Studio version of the component. I think that's pretty much it on that page, our history. So, yeah, done code plates. Sorry about that. Not all the decisions are up to me. But it's on code plates. It's on code plates. Sorry, Ryan. But the repo is Git, so, you know, close your eyes, clone, you're good to go. Some of the things that we do, we'll give you nightly signed builds. So when the code base changes enough that we need to do a new build, we'll prop it up on our CodePlate site. You can download the latest build and install them. I've only actually heard of one installer issue, and that was reported just today. And I think we're getting 10, 15 downloads at a time. So there have been plenty of downloads, and it all continues to work. So it's pretty reliable, except this one installer issue, which I'll get to. In the code base for the open source, there's an extensive test suite. We did a lot of work, Lincoln did a lot of work in April in order to make the thing regression testable. When you do your submissions, if you don't add tests, Lincoln will remind you that you should add tests. Sometimes I forget to remind people that they should provide tests, but Lincoln always reminds them. We're active on the submissions, the discussions, and the issues. So if you close your eyes and imagine you're using some website that's not spelled CodePlex, and you ask a question, it's very likely to get fairly quickly answered. We also try to work with the other open source projects, particularly the Powertools, which are so cool it's unreal. And the open source Visual Studio components still work with Powertools when you install the v6. So you won't have to throw away Powertools just because you're debugging our language server. Thomas's Toslin thing, he's added a bunch of really great APIs. We want to bring those back into our language service really quite badly. So if anybody is interested in doing that, make up a submission and it will certainly get considered. So how's it going? Like I said, we're about to ship Loop 2. That's got real open source contributions. It contains quite a few community pull requests. We've started a fork for FSharp 4 contributions, and there's a user voice that you can go to discuss the features that you want with, well, all of us, but most specifically with John. The 3.1 fork is about to get all of our upper stack stuff. And we're getting a decent quantity of high quality pull requests. Mostly they're not junk. In fact, I don't think I've seen a junk one so far, except for one that Vlad submitted right at the beginning. And I expect better of Vladimir because he's doing this. We've applied 18 of the community pull requests to the code base. So that's 18 changes that wouldn't have happened without community doing their thing. We've currently got 6 open. 2 are FSharp 4 features. The other 4 will go in the next week. Oh yeah, the types of submissions that we've got. I forgot I even done this. So the submissions that we're getting some great bug fixes. Whether set breakpoint in a quotation is a bug fix or a feature is kind of arguable. I would go either way on it, but null ref in miscomprehension, that's flat. Internal error, that's flat. T-farm, that's William Smith, right? Inline optimization using structs, that was our first pull request. I was super pleased when I got that one. And I really wanted to make it the first one that we submitted. But it took forever to get the license side. So that one went in really later. That per progression in 3.1, that's flag. In Dev 12, there was a pretty horrific performance regression for overloaded functions or something. The guys that reported it were saying, we can't go to 2013 services because our build's taking so long. And Vlad got on that and he fixed that and that's really great. And again, these are all stuff that we probably, without the community digging down and finding this stuff, and we wouldn't have, we quite possibly wouldn't have got to it, certainly by now. Then we got some new language features. The shebang is about to go in. That's of no interest to Windows users whatsoever, but the Unix guys Apparently they've got a shell that looks at the first line and does some magic. The request for that, the guy said, bear with me, I know this looks like this isn't a Windows thing, but it would be really great if you could do that. And we said, of course. Of course, man. You send us some code, we'll be fine with it. He sent us some code, we had some comments, he iterated on it, Lincoln made him do some tests, life was good. And then we've got, some cleanup. Don apparently likes nice folders in his Visual Studio when he's looking at stuff. So we felt that it was very important that we spent some time doing that. And then we have this hashes Silverlight from back in the day that was effectively dead code. And so we took that out. And more tests, if any of you have a few moments. Write out some more tests and send them in, because more than anything else, that's fabulous. So they're the type of submissions that we're getting, and I think that's pretty much me done. So, anybody got any questions? There's going to be at least one about the license, right?
So are you using this CodeFlex repo for your internal changes that you're doing to your internal development work?
So,
just kind of curious. So
the way that it works is we're still part of Visual Studio, so we still use TFS internally so that we get propagated through to all of the Visual Studio stuff that goes on. But those changes are immediately mirrored via a staging server that we have out to GitHub. So the only time that code doesn't appear on the open source is when it's sitting in somebody's shell set, ready to be submitted. But the one piece that's not open source is the build stuff, and trust me, you do not want to see our build stuff. Our packaging stuff. It's wits and it's nightmarish.
Yeah. So there's the elimination of all those like big Silverlight tabs. So for instance, in FSharp I or like 4 months ago, it used to be the case that there was like a lot of objects depending on the Silverlight. So could we clean up with regards to that, or is it just the code was gone?
The code was probably dead anyway. Anything that was inside of hashes Silverlight was likely dead. There were some places in FSharp Core, I think, where that wasn't the case. But you know, the cleanup eluded all of the code that needed to be deleted.
Also, there's also the GitHub repo as well. Is that just American?
So you're talking about the FSharp open source repository on GitHub, FSharp.
Yeah.
You can think of that as the cross-platform repo. It's that repo that the Xamarin guys pull from and push to. And they had to, because for most of the last few years, that's been the repo for FSharp. For now, you should consider the CodeFlex repo as where you go to change all software that goes into the Visual FSharp tools. It's very likely that you'll have some cross-platform stuff or some mono stuff, and it's very likely that that will also come through our repo. That really just depends on how badly it messes up our Visual Studio stuff. But we want to take as much of the code as we can. We also want to bring back Thomas has got a second fork. even though Thomas and Don are good buddies and stuff, we've got F#, we've got Thomas's repo, and they don't quite align anymore. We've got to bring that back at least as far as F#, and I want to bring Thomas's stuff back into ours because the language service changes that he's done are really, really cool, and we want to build our editors, IntelliSense designs on top of that stuff as well. Particularly since we don't want the Powertools to repass every damn file that we pass in order to provide their version of IntelliSense and coloring, as well as our versions. So we will, over the next however long it takes, make sure that that happens. And if anybody is really keen on that, they should definitely start working on it. Anything else? Yeah?
So does the contributor agreement work kind of like Clojure, where I print out a form and sign it and fax it and send it off and then send a patch, or?
I believe you can sign it on the website. I've never gone through it. The contributor agreement has some scary properties. If there's anything about it that you find off-putting, then you should talk to us, and we'll talk to our lawyers, and we'll try to figure out how to get it worked out. It pretty much works out for everybody who contacts us. But it does have some scary qualities. Will Smith, he had part of the agreement is your employer says that he doesn't own the rights to any of the work that you're doing for open source. Some people's employers think that they own everything that you do. So the intent of that, and I'm no lawyer, but the intent of that clause is so that you can say, yeah, you know what, it's perfectly okay for me to give this code to the open source community. And you're really asserting that, so that we can then make sure that everybody's got it. So, but the license agreement, I have to admit, is a little bit scary. And you should work with us if it's tricky for you. For Will Smith, it was tricky.
Is it anyhow simplified for? No.
Internal contributors are fine because their employer is quite happy for them to contribute to the open source. So it's fine. It's relatively easy. You just get your boss to look at the web page and then you do whatever it is that you have to do. Whatever it is that the site says you do, you do. It's fine.
No, contributions from Microsoft.
Yeah.
You still have to sign the CLA.
You have to sign it internally. So that's an interesting thing about the way that we're doing this open source. And I contract to MS Open Tech. I'm a full-time Microsoft employee, but right at the moment I contract to MS Open Tech, which is a subsidiary of Microsoft. And so Microsoft employees who want to contribute to MS Open Tech have to sign the MS Open Tech license agreement. But it's very straightforward, and you can talk to the lawyers. Your manager can talk to the lawyers, but he shouldn't need to. He should just say it's MS Open Tech. Of course, okay. So Vlad's been through it. Don's been through it, and Don's a little trickier because he's a researcher in Cambridge. So. Yeah. Lincoln doesn't have to.
I haven't done it.
And he's not in MS Open Tech. And that's because our team is collaborating with MS Open Tech on the whole Roslyn open source thing. And so members of the team can do what they call de minimis contributions to FSharp or to Roslyn without going through the Anything else? Okay. Well, thank you. Okay.
Maybe not related to additional. Is there anything about integrating FSharp with ASP Max you start finding out later?
It's on our radar to figure out how that's going to come together. But right now, the ASP VNext guys are still sitting around trying to figure out what they look like and what they're doing. So when that stabilizes a little bit, I think that we'll probably get involved in the party. For sure, it'll happen. It's just that right now, it's not something that we're spending our resources.
Thanks a lot, Kurt.
Thank you. So you can tell Ryan and copy my.
Now we gotta switch over. We're gonna switch over the stream and everything. So if you guys want to take a pizza break, quick bathroom break.
We would have to wait.
Yeah. Are you also or no?
Hey, Kurt.
Hey there.
Oh.
So you're on that, sure. No, I can see it.
I still see Kevin's screen on the live feed.
Okay, Kevin's closed his laptop now, so that he's not connected anymore.
Okay, it should go away at some point.
Okay, so.
So that's
Yeah.
I know I'm in their website.
So is it like a screen share thing?
Yeah.
I used to see green screen now.
Okay, Kurt, you're all set. Your stuff is showing up on the live feed.
Okay. So should we just tell you when we're ready to go?
Oh, we're rolling.
Okay, great.
No, I don't think you do anymore. Simon said.
All right, we're gonna get going again here. This is the right thing. A couple of months ago again.
Is this what I'm talking
Ooh.
about?
Pretty good. Oh, they're known for it. Not outside here. Not outside here.
Oh, really?
All right, let's go ahead and move on to our second talk. So our second talk today is by Curt Nichols. Curt is a regular at the FSharp user group here. I've seen him a bunch of times. He's a principal software engineer at Soundmetrics, and that does high-resolution imaging sonar, which I don't know much about myself. Hopefully we'll get to learn a little bit. And he's been doing stuff all throughout the software industry. He's developed software for a lot of different applications. So he's got a lot of experience, and I'm interested to see what kind of insights he has about where FSharp can play a role. So let's welcome Curt.
So I guess I don't have to introduce myself now. What this talk is right now is basically a report from the field. describe a bit about how we're changing our code base, and a few comments and illustrations about what we've been learning from that. I work for a company called Sound Metrics. We're over in north of Bellevue. We're a manufacturer. We manufacture sonar equipment. Specifically, we manufacture imaging sonar. In movies and whatnot, you've probably seen submarines sending out pings to find things and whatnot. There are also fish finders, are also essentially sonar, so you can look at the bottom of the river, the lake, wherever you are, find fish. We work a little bit differently. We actually use acoustic lenses to focus energy that we send out. That energy, if it finds something to bounce off, returns to us, comes back through the lens, gets focused, and we reassemble that into pictures. Something that's a bit different about those pictures sorry about this, is they're taken in a different plane than, say, a photograph that you shoot with a camera. A photograph, if this is a photograph that I shot with a camera, field of view is normal to my sight, right? That I'm taking a picture of something like this out here. With sonar, the energy actually goes out in the same plane that the sonar is looking at. So if I were to take a sonar shot in here, if we were underwater, that is, I would be taking a cross section across the line this way. If I rotate the sonar, I'd be taking a cross section this way. And that image that I take here is in this plane, right? So when we look at it, we're actually turning it up on end and looking at it as if we're in plan view. We're looking top down on the field that we're taking an image of. This, for a moment, it's a tire. See if I can start it here. Please. Oh, come on. Oh, this is terrible. Give me just a moment. There we go. Of course, it works in rehearsal, but I'm going to try to find another way to show you this. Nope. Okay, this is disappointing. I'm sorry. So this is actually a tire. We're kind of looking top down on this tire. I see something threaded. And what happens when we take that sonar and rotate it along this axis is you actually get to see a different dimension of the tire. Again, it's different than taking photographs, right? We're not looking at this, we're looking at this plane. And so we rotate it. It's an entirely different thing. Okay, that's too bad. All right, this is an image of a riverbed near a fish there. A common use for imaging sonar is actually counting fish. Fisheries, or these fishing industries use it to control fishing seasons. So salmon is shot, and the state says, so we're going to count the fish and decide when the season opens, when it closes. Because we actually know the distance of things, right? Something you don't get with photographs so much. We can actually measure the fish, right? So they spend days and days recording fish going by, counting them, and measuring. It gets a lot easier when we apply some image processing. There's 4 fish here. Think about, we send out sound, we know how long it takes for the echo to come back. We know what that distance is because we have focused lens. We can also measure the width of fish in here. That kind of processing, this background subtraction, takes some model. Every frame that comes in, we're not shooting stills all the time. We're shooting a lot of moving pictures. Every frame that comes in, we into a model that we can then eventually apply to the images to remove background from the image. One of the issues with that is that it generates data. If you think about it, we're updating this image constantly. We're updating the model constantly. If every time we make these updates, we have to copy the whole model or the whole image, we're now generating a whole lot of memory allocations.
Can you speak up, please?
Sure.
Thank you.
So tackling mutable state. I don't know if you, when you first saw the title, if you thought, well, what's this about tackling? It's a bit of a weasel word. Did I mean to say eliminating? Because now that I'm a member of the cult of immutability, that should be what I'm doing, right? Did I mean embracing? Because why would we even be talking about it? Maybe hiding? Maybe reasoning about it.
I assumed it was a fishing pond.
What's that?
I assumed it was a fishing pond, I said.
Yeah, I wish. Now you mentioned it. Okay, so immutability. We get benefits from immutability, right? We have more easily understood code. The data is not changing underneath while we do things. We don't expect it to change. It doesn't. It simply doesn't. Compiler makes sure that you know what's going on. It's easier to reason about the code, partly because of what I just mentioned. We can look at the code and know this is this, right? That's kind of a attribute of functional programming in general too, that if you pursue the whole notion that your functions are pure, that stuff goes in, stuff comes out, nothing else changes. And immutability gives us a nice little boost for thread safety. If the data isn't changing underneath us, then we don't have racing issues because the data doesn't change. Downsides. Immutable data structures can bring design challenges. If you think about constructing data structures to represent a tree, and you want to be able to update that tree, you get to rebuild the tree. You can reuse parts of it, but you have to reconstruct the tree to add nodes into it. CPU cycle spent doing that can get considerable, depending on the problem you're solving. And especially in my case, the increase in memory use is truly noticeable. If I have a process if I have a function to process an image, I've got an array of bytes, each one, in our case, you can see we don't have color because we're using sound to represent images. We have 1 byte per pixel that represents the amount of energy that came back. If every time I have to transform that array, I'm making a copy of it, I'm now doubling and tripling the memory load that I use. Garbage collection is not free. Allocation in CLR is pretty darn fast. Garbage collection is not free. Complication of this is that our data is large enough that it winds up quite often a large object heap. And that gets collected a bit differently than the generational heap. I know there's been some changes to that in .NET 4.5. My profiling says we still have an issue with that. So already I'm getting into a compromise area, right? That I would like to have immutable data so that I can just reason about the code a lot easier. The more mutable data I have, the harder it is for me to look at the code, to maintain it, find problems with it, and to potentially move it in the future. Where we're coming from. I've introduced the use of FSharp this year in part of our product that does a lot of work. We have a fairly large C++ code base that does image processing work. I can't necessarily promise that all that C++ is going to go away because a lot of it's pretty well-performing code. However, a lot of it probably will. Our legacy code, I think, sometimes looks something like this. And even though it was C++ and it had a lot of mutable state, there's actually multiple threads going on. When you have just basic code, it's easy to reason about. Within a month, we're up to about here. Another client comes back and says they need things. 2 years later, we've got something that I can't possibly reason about. We have multiple threads hitting it. We've got multiple pieces of mutable state. Arguably, there are other reasons that this happened, and they're largely around design issues. But we're back to something that we just can't reason about. We can't sit down and say, if I make another call here from this thread, what will that affect? I can't answer that at all right now. About 3 years ago, maybe a little bit less, I did a little prototyping work. Took our Dataflow, which essentially, we have the sonar sensor in the water. We have an Ethernet connection from the sonar up to topside PC. So we've got PC on the boat or on the bank that's running software that we can use for visualization. The pictures that you saw earlier are from that topside software. Data comes up from the sonar, we assemble that in frames, we have to do some processing on it so that it actually looks like something to the human eye instead of a jumble. And then we perform some other transforms and processing for the modeling and display it on the screen. In looking at how all that worked, and we were trying to also answer the question of how do we offload some of these bugs we had, which were largely around synchronization. Started looking at Dataflow graph. The .NET has a test parallel library, and one of the more recent parts I think that was added at the time was the Dataflow library. Dataflow library allows us to build small blocks of code, and by and large we can reason about them pretty well. If we draw the block here, we've got an input here, we've got an output. In the middle of it is a structure that the library provides that allows us to essentially plug these things together to compose them into the Dataflow graph. The root of the Dataflow graph, you would post or send a message into it, and each block throughout the graph would do its kind of processing. Depends on what you tell the blocks to do. You provide the code, the blocks help shuttle the message through the graph and get the job done. So we associate some code with the block. Here I'm just showing a transform block. It takes something in, returns something out. How the transform works depends on what function we pass into it. I've got a little A to B function I've attached here. In code, it looks something like this. We construct a transform block, passing in a function f. F defines what this transform is. Then we're off to the races. We post a message to the block. Block does its transform. Out the other side comes, in this case, a P. There are different kinds of Dataflow blocks. There's a buffer block, so you can post things to it. things can build up in that buffer while the receiver of those messages does its work. It may lag behind, it can go and grab something out of the buffer. So, there are action blocks with multicast blocks. You can create your own kinds of blocks should you need to. In my case, I have a T block that allows me to split the data flow so that I can actually have multiple branches in my graph. So, like I said, we can compose these blocks. We wind up with a graph. This is not a terribly interesting graph, but we can see that from left. Hello. From left to right, that we have input into the graph, message travels through, they get transformed. In this case, I'm going with the A to B to C to D, and F as we come out of it. We compose these graphs. If we're looking at Dataflow APIs, kind of like this. Here I've got one constructed, one data block. I've got another transform block, and yet another transform block. You might in real life not see this many transform blocks stacked up in a row because it would be pretty easy to put all the code in one block if you just didn't transform. But the magic in building a graph is in the link to here, right? That I'm starting from the left side. I've got this first block that I built. I link that to the second one, link the second one to the third one, and so on. That's how I build my graph. One aspect of the link to API is that you actually have to have the way I've drawn it here. You have to have the right-hand block available in order to link from the left-hand block. So in fact, the data flow is left to right here. Constructing the graph actually looks pretty well to right to left. And you can compose these into larger graphs. Here's a T. I'm going to carry a piece of data through on this longer segment here, unmolested. We're going to do a little more processing on the other branch. Actually T again, and in the end we'll just wrap it all up. Unify the data in one block and record what we need to disk. Because the data flow blocks share interfaces, they have a target interface and a source interface. Essentially, any block that you can think of or construct yourself that implements those interfaces can be composed into one of these data flow graphs. And because they also talk that way, I can rearrange my graph as needed for either functionality or performance. So, transfer block takes an A to a B. There's no state implied here. You've got a pure function, you're taking stuff in, putting stuff out, nothing else changes. As I mentioned before, we have some difficulty with the amount of data that we produce. Sometimes it's actually much easier for us to just keep mutable state around. A lot of problems can actually stay fully mutable. I see tweets and posts about people that have taken their system and gone fully mutable with it, and that loss, we have a little bit of an issue that we run into performance-wise and resource-wise. On my desktop, I have a very fast machine. I can do a whole lot of garbage collecting. My customers don't. They're often on modest hardware out in the field, and it needs to work quicker. Alternatively, if we get rid of garbage collection altogether, through perhaps an infinite amount of RAM, we wouldn't have to worry about it. But right now, we can't do that kind of thing. So let's talk about how we get state into this data flow graph. This is not the kind of transform that we use, but it's an interesting little example. Memo-wise, it's kind of functionality that you say, here, I got this function, I want to increase its performance, so let's do a little bit of caching, and when I ask for the same thing twice in a row, you just retrieve the cache result. Presumably, F in this case is the function that does the actual transform. Presumably F requires enough CPU power, enough time on CPU that it makes sense to do this kind of caching. In this case, we could probably stay at that when I'm talking about all the things that are wrong with this. I've used the dictionary from the .NET framework. It is fully mutable. There's nothing magic about that. It's just a big old mutable dictionary. This memorize function takes the F function and returns a function. That function returning takes a value, checks to see if it's got a cache result. If not, it computes it, stores it in the cache, returns the result. This largely works, but there are probably some problems with it. I don't want to take a stab at it. That's true. That's about the last one I expected here. This is a cache without an expiration policy, so long as you keep this thing around, you will just accumulate more memory.
If there was an exception, you're kind of in a problem, essentially.
Quite possibly.
If you check to see if it contains X and then later, I mean, you know, it can change in between the read and the date.
Okay, so race condition. Yeah, it's not thread safe. We got a lot to it. We can avoid that. In this case, it starts to function, I think, in a fairly rational manner, right? That if I want to talk about whether this is, obviously there's mutable data here, right? We're not saying this is a pure function with current side effects. But to the outside world, they don't know if the mutable data is there, right? I can pass in a 2, get something back. I can pass in a 4, get something back. Whether you wrote it this way or you wrote it this way down at the bottom, I won't be able to tell the difference as a call, right? That memorize of F, just return the F, return the original function. It should always still behave the same way. If you pass in a 2, and the function that you're memorizing is square, you should get back a 4. In the bottom case, because you're actually calling the square function. In the other cases, because quite possibly that result is cached. We can't tell the difference from a caller's perspective, which of these it is.
Unless res is mutable.
That's what?
Less res is mutable.
Right, and I'm working on the, let's talk about squaring X and that kind of thing right now. Aside from that, what we will observe if, say, we're just squaring numbers, is we might be able to observe that there's some memory usage. We don't have to cap on cache or an expiration policy, and it may be faster to use our memorize function instead of the original function. Logically, they behave pretty much the same.
Isn't there also the problem with X is a reference type? You have to deal with equality of X?
Yeah, and I think that, well, that's not quite your point.
Yeah, F should be a pure function, right?
It is, yeah. This code, the 2 large examples, the inference falls out. This I typed into PowerPoint directly, so it may not compile it out for you. Right? Okay, so there can be some issues with this, but we can actually talk about and reason about it, right? If we can contain immutability, and say it's only right here, we can actually reason about that and get to a point where we think we've done it well enough that it behaves the way we want, right? The outside world doesn't know that mutable state is there anymore. We're getting our functionality. So if you keep it small enough, you can actually reason about it, try to determine what is going on. So what are we doing here? Trying to hide mutable state. For, say, our modeling functions, I can't just keep creating new copies of it. So we're going to do just like I showed with the memorize function. We're going to just hide that little copy in mutable state, and then we have to reason about it, figure out whether we've hidden it well enough to function in our system in a way that we don't have any concern about it. Mostly it's got to function correctly. Can't be any race conditions. We're going to wind up mangling our state if we have race conditions. We can't leak the mutable state out of it. Right? The code that produces the result can't pass out the mutable state because now someone else can change it too. And then the biggest problem probably is that every time that code changes, we have to go back to reinsert all these, examine the assertions here and say, okay, we still believe that it's in this state where we can trust the code. It's not, there's no silver rule about it. It's mutable state, but the more you can contain it, the more you can localize it, the more you can reason about it. And in this case, what I want to do is be able to take that function, put it into my Dataflow block. But my Dataflow block wants a function that looks like A to B. And if I have a state hang around, it's another piece of data. I'm going to get this in. This is the signature of my function F now. I have a state that goes in this case a ref cell. Then I have the integer input, integer output. What I really want is this signature. That's what the Dataflow block wants. It's a transform block. It wants one type going in, one type going out. How do I get that? How do I get from having state that I need to pass in as an initial input to make that go away? It happens that we have a handy little solution that I can query my function F, hand it the state, and the result of that is now it's got the right signature to use. And what happens here, we've got F passing that ref cell initialized to 0. That ref cell is now used by the new query function. And so long as I'm nice about this, nobody else in the world has a reference to that ref cell. Nobody else can modify it, so long as my function doesn't somehow pass that state, that mutable state onward. No one can touch it. So we've set up this condition where we now have a state that is integral to making this code perform, and it's hidden from everyone else. So there's probably a lot of reason to avoid what I was just talking about. If you can actually get all your data immutable, only modify in the places you need to be, that's great. If not, we wind up having to find solutions. There comes a point in the work that we do that we start looking at places where we need to share mutable state between various pieces of code. I've labeled that as passing mutable data structures. We have multiple blocks in the graph that want to be passing mutable data structures around. We've got a much bigger problem. Mostly don't do it, which is probably what some of you are thinking about, what I've been talking about for the last 20 minutes. But in this case, we can't control that mutable data at all. If you're exposing the data from one place to another, anyone can get a reference to it, anyone can change it. It's going to be a big maintenance headache. Change the design. If we have 3 blocks here that are using mutable data, any data that we don't want to sneak out, don't be passing around. If you can refactor your design so that the 3 bits of functionality all sit in one block, you don't have to expose that data outside of the block. that effectively limits the effect. Another method that you can use to limit the visibility of any piece of data is essentially to wrap it. If we have a module into which we can put these 3 pieces of code, we can also create a type in that module, make it private. These 3 pieces of code have access to that type, but no one outside the module can see it, so you have no way to pass that piece of data out of the module. That way you limit accessibility to the data. So, mostly, if you can't avoid mutability, practice pinhole mutability. Keep your mutable state private. Don't let anyone see it. Don't let anyone change it. You have to guarantee no race conditions in your code. You know, these are things that immutable data, when you're using it, it doesn't happen, right? You get away with it. Keep it small, maintain the ability to reason over your code. Keep any code that interacts with mutable state as small as possible. You need to keep it in a tiny little pen and keep an eye on it. How are we doing on time?
20 more minutes?
Yeah. Okay. Okay, let's get the we'll talk about immutability and get on to building a graph here. Here's a graph before. This is a small one with 3 boxes. They're all transformed. We're going from A's to B's to C's to T's. This is how I build it. Now, in this case, I'm going to build it from right to left. Right. First transform block, it's constructed 2D. It's a function that converts from C to a D. So I built the rightmost block. I'm going to build the middle block. It's a B to C, and I can link the 2 from B to C, C to D. I build the first transform block and link it to the second one. It would be nice, while doing this, if we didn't have quite as wordy an API. You know, if we're able to compose some functions together, can't we do that with Dataflow blocks? In this case, what I'm showing here is when a function is composed. These don't make a Dataflow graph, they just make composed functions. But if I can compose constructors of Dataflow blocks, then I can compose a graph out of those. Now, I want to be composing right to left here, so if I take my constructors, compose them from right to left, now I can create the rightmost block, move left forward through them, linking them together as I go. Bit of scaffolding in building up these things. Each of those constructors that I have produces enough scaffolding so that the predecessor block to its left can talk to it, can link to it. There's actually 3 pieces we track. iTarget block is the Dataflow library's interface for how you look, how you behave when you're a target of messages, and someone can hand you a message. In this case, leaf nodes is a list of nodes in the graph. We track what the last nodes in the graph are, because leaves are interesting to us for a reason I'll mention in a moment. And then the disposable lists are disposables that we build as we link the graph together. Those links between the blocks are all disposable. So it'd be nice if we cleaned up when we're done with the graph. The leaf nodes. Let me go back here. So this rightmost transform block here, the C to D, it's the last block in the graph. Right? It's the leaf node. When I shut down this graph, I want to be able to tell the whole thing to shut yourself down, and I want to know when it's complete. Right? In our case, we have data coming in from a sensor and it's out in the water. We are doing our transforms on the data. We're recording things to disk. We want to know, okay, when we shut this down, we're going to flush all the data through the graph, get it to disk. Dataflow library has a complete feature. You can tell the graph, okay, you're complete now. And you can propagate that notion of being complete through the graph, and this automatic propagate if you tell it to. So what we can actually do is when we have leaf nodes in the graph, we can just watch the leaf nodes. When all of our leaf nodes have gone to a complete state, then we know we can tear down the graph because all the data is on it. That is how we wind up with a list of leaf nodes in the scaffolding here. This little nightmare is it's a means of creating a transform block out of a mutator function. Bind transform, first parameter, well, the only parameter is the transform function. Transforming from T to U. And what the bind here does is it returns a function that takes a scaffolding and returns another scaffolding. These scaffoldings represent Dataflow blocks, right? So what we're doing here is we're returning a function that takes scaffolding from the right-hand node. It's constructing a new Dataflow block, and returning its own scaffolding, and this chains from right to left. But as we build a block for a scaffolding, if we go to the left, to the constructor on the left, it creates its own block, links to the one on the right, and then returns its own scaffolding. So that way we propagate this notion of what's on the right all the way to the left. The return here, just like the scaffold type up here, we're returning the target interface on the block that we just created. We're returning any leaves that we know of. Some of them may come from the right of us. If there's no one to the right of us, then I'm a leaf I need to return myself with. And we append the list of disposables to our new disposables and send it on to the left. This is much the same thing, except it commits the crime of having state. First parameter is a function to create the state that's going to be casting for this transform. Second parameter is the transform function. We saw this a bit earlier. It's got state in, got T in, and U out. It returns a function that returns scaffolding. This guy does its own work to create its transform block. Again, creates scaffolding, propagates everything out to the left again. This code, by the way, I've got up in GitHub, and I haven't made it public yet. But if it appeals to you as something you want to play with, I got the URL to it at the end of the slide deck. So I just showed some bind functions that transform our mutators into Dataflow graphs in a very general way. These are actually more application specific. I'm making an image processor node, and in order to do this, I pass in a function. Takes, in this case, a mutable frame, and returns something else. The make data assembler node makes use of state, and much like we've seen before, when I find it, I'm passing in a function that creates the state. In this case, again, it's a reference cell to an integer. I pass the transform in, and in the end, this creates a constructor for a Dataflow node. Using them with something like this. These are not Dataflow nodes that I'm composing here. These are constructors for nodes, right? We build them right to left, and so I'm actually starting with a terminating node, a node that specifically knows that it's a leaf node. We build it right to left, and finally we assign that value to construct graph. Construct graph is not graph, it's the constructor for the graph. When we invoke that, we get the root of the graph. We actually get one of the scaffoldings back, which contains the reference to that root node as a target. We have the leaves, and we have the disposables. And now we have means of actually posting things into that graph. We can watch the leaves to see when they actually complete after the graph is done. And we have the disposables that we can clean up after it's done. We can make different kinds of nodes. Make a T node that allows me to bifurcate the flow of data. There are other kinds of data flow blocks that do similar things. There's a multicast block. They have all of interesting properties, and some of them don't quite fit our use cases. That when I want to T the data, I want the same data to go through both branches. And I'm just trying to find who's most available to process the data. I really want to push the data to every one of our nodes. And so in this case, our MIT function here takes a list of graphs. When it receives a message, it sends that message on to, in this case, both of the subgraphs. So again, same thing. Invoke construct graph here, we can post a message to it, and put wait clean as a little helper function to tell the root node that it's complete. It waits for all the leaf nodes to get to the complete state. At that point, we know that all the data is propagated through, and we can clean it up, take care of the disposal as well. That is that. That's what I got for you. This GitHub repo. I'm going to make it public tonight, so if you want to go play with things. That's actually working code. You can sit there, trace it in whatever sequence you want. I found the notion of creating constructors that can create the nodes themselves allows me to compose them a lot better. So, have at it. Take a look at Dataflow.
So is everything you showed us something that's in production at your company right now, or is it side projects?
They're not side projects. They're first-class projects. They're not quite in production yet.
Plan is to get that stuff. Is that sort of like an overhaul or a new component you're adding?
It's a bit of an overhaul. I mean, when we started with legacy code, that current picture of all the ins and outs is really what tends to happen, right? And it's very difficult for large projects to be responsive to customer needs if that's what you have. We're moving toward componentization, so we can take our components, plug them together, make new things with customers. We have, people counting fish, we have people looking at the footings of dams for damage, search and rescue operations. They're focusing the Arctic Circle, trying to do their thing, exploration and oil. They all have different needs. The easier it is for us to create those components and plug them together, the more we can take care of them.
Does your profiling show that you're not progressing perfect?
Oh, no. There's probably a fair amount of talking to do actually about just where we've been going with it and how we also know. As I mentioned, the original code base that has a lot of C++. The C++, the Microsoft C++ compiler is pretty good. And there's a lot of profiling. You have a lot of control over playing with memory. Whereas I showed an array of bytes earlier. How do you manipulate it and manage code? It can be slower. We have ways that we're working on to get through that. I would like to be able to take some portion of that C++ and just pull it all in FSharp. In particular, the image manipulation parts, that's going to be a tough sell. There are parts of that show up in the profiler that I don't expect to show up. Things like pointer arithmetic. Why is that a hotspot in the profile section? I'd really like it not to be. But it's open source, so
So the things that you're posting to your root node it's like a big image, right? It's a big map or something like that.
It is.
So it goes in, and each step has exclusive access to that it's mutable, right? This big bitmap. What happens when you T? Do you make a copy of the bitmap, or?
By the T, it's largely immutable. I say
Okay.
largely. There are actually some changes that have no road, but they're no longer image processing type changes, right? So if I have an identifier on that piece of data that has to change at the end, I can fake that. I can handle that. I can recompose an object with a new identifier on it without costing me a whole new array.
So you have a set of images then between these blocks that
Yes.
but you can re-architect this such that really what you want is the end block, right?
Okay.
So you re-architect this rather than these having these intermediate chunks of memory. When you call this function, it then calls the previous function, you know, and on back to the original source image, right? And you'd have effectively the same result.
I'm not sure what you're getting at.
Well, I'm saying that you could do the same operations without a bunch of intermediate images by having each of these blocks that take, say, an input image and output and have an output image, rather than asking it to get its input image from, you know, an image. If it in fact then calls the previous block to get its image or its output, et cetera, like that, and therefore you have this memory of all these.
Right. In fact, the image processing parts are much more tightly bound than what I showed up here. Right? There's a lot of work to be done there. When you're dealing with, you know, it's not HD video, but it's still a fair amount of memory that we're working through. When you're dealing with that much, you know, face-to-face and attention that's going on, if I have 3 different level processes that I'm applying to an image, right? Apply one to the whole image, apply another to the whole image, and a third, I'm evicting the whole image from cache every time, right? And if I have functions for that modeling that can actually be friendly, that is, if they don't have dependencies on each other or on vertically neighboring pixels, I can essentially treat it as scanlines, right? And I've got a row of pixels, and I can actually recompose what's going on. Instead of having a function that takes the whole image, I can now say, well, the thing that's going through is a scanline. It's a row of pixels. And then I can compose these functions not around the whole image, just around the row of pixels. I can compose them together. And this is kind of, I didn't get into this tonight, but it's kind of cool that I can inline those and wind up with this tight little piece of code that's all focusing on caching, essentially. And all the work is hitting once in cache. So we take one trip through the image instead of 3. What it looks like in the code is that I have 3 functions that compose it. But it's really doing something better than what I hoped for. I come from an object-oriented world. You might get that stuff. But the fact that I can look at that function composition, see what the compiler is generating the release beds, that, oh, it's actually this big now, not bouncing around the cache. It's pretty fun.
So regarding Dataflow, I was curious how many different types of blocks you're using to transform in T compared to how many that software provides as a whole.
Yeah, so the Dataflow library provides more than I use. T is one that I composed some other things. The library actually provides a nice little mechanism that says, if you provide us with these things, we can create a new block for you. That's essentially what I do with T. There's a multicast block, and I'm not going to be able to remember them while standing up here, but you know, there's I think at least a half dozen blocks in the library that do interesting things. Things like multicast, I believe, it's got multiple clients that it links to, but it's not going to send to all of them. It's going to find the first one that's available to process a message, send it to that one, and then it takes the next message and moves on. That's not the kind of thing that I need to do. Essentially, the kind of things that we use, there's a place where we've got a buffer so that we can let things float around a bit. Transform blocks. There are action blocks, which they don't transform. You just have an input and you can perform an action. So you have an input unit as your result. I actually take the action blocks and use the input as the output so I can use them, compose them somewhere in the graph as I wish instead of just dead ending the data at that point. I've got the T. We don't actually have the join block yet, but we will. And that's about it. That's all there is. Some of the funkiness that can happen with a Dataflow graph. We're pouring a lot of data into it. The parts up front need to be fairly high performance. Parts behind can kind of lag and adjust as things go on. And once you start doing that, once you put a buffer in there, you start having to deal with, well, I'm responsible for this now. What happens if the part at the end just can't keep up at all, right? So it kind of changes the nature of some of the problems that you have to solve. Somewhere in the graph you have a bottleneck and you need to either start dropping data or adjust your parameters. Changes the problem because now this buffer block is essentially in charge and you have to determine how to look at it and say, we're in this condition that we don't want to be in, let's get on with it. As compared to procedural code where you might say, no, put it in this list and check out what listed. So the plumbing for the Dataflow graph is not on code. So that kind of adjust. Or not that I detect what's going on.
Thanks a lot, Kurt.
Thank you.
All right, well, that's what we have for you tonight. Thanks everybody for coming out and supporting the group. If any of you guys have ideas for talks that you'd like to give, feel free to get in touch with me or Wanzak on the meetup.com page, or if you work at Microsoft, find us in the email list.